Okay, so how many guys read this? Okay, how many people took freshman chem from me or inner chem? All right, yes, thank you. Okay, you guys can ask. Hey, somebody in the back did too. They didn't raise their hand. Where'd they go? All right, there you are. I'm going to call on you. All right, how many of you read this book? Yes. Okay, none of the chemists. Thank you, guys. Nobody. So these, what are you, literature people? Okay. I, Robot, this classic book of Isaac Asimov's. Actually, most of you probably saw the movie and didn't actually read the book because Will Smith, it was a gorgeous movie. So he had 3 laws that he proposed in this book, actually. It's called The 3 Laws of Robotics, if you're an Isaac Asimov fan. Robots can't hurt people. Robots have to obey people. And, okay, if they follow those 2 rules, then they can do what they want. And so protect itself and don't let itself come to harm, but follow the first 2 rules. I work in nanotechnology, and so I don't really do robots, but we try to make things that are like robots, except they're really small. So if you have a robot, even this, actually there's a nano robot called a nanobug you can buy at a toy store, but it's like that big. It's really not nano, and if your kid plays with it and it crawls across the floor, you can stomp on it, get it to stop crawling, you can pick it up, you throw it away. When you make a nanostructure or a robot to swim through the body, looking for cancer, for example, one of the areas that we work on, how do you pick it up and stomp on it when it's going the wrong direction? Or how do you tell it to stop doing what it's doing? Or when it's done doing what it's doing, which is hopefully curing a disease, how do you get it to turn off and go away? And so I came up with what I call the 3 laws of nanorobotics. And the first is they're simpler than Isaac Asimov's, because he's a lot smarter than me. Go where you're told to go. So that's one of the things we do. I'll give you a little insight about how we do that. And actually, it turns out it has to do with chemistry. And in the biomedical field, this is often referred to as no off-target effect. So really, there are nanoparticles that are used today for people. If you're a woman with breast cancer, you may be treated with Abraxane. It's a nanoparticle that treats cancer. It's used in the clinic. There's about a dozen drugs now that are made out of nanoparticles. And an off-target effect is if you give a patient any kind of drug, it's going to go to the liver, the kidneys, or maybe into the brain or the heart, and that's not where the disease is. And so it's going into a place where it's not supposed to go, and usually it's showing a toxic effect, and so that would be what we call a side effect, or what they refer to as an off-target effect. Do what you're told to do. So that is, go kill the cancer. Don't hurt the heart muscle. And so typically in our world, that's release the drug. So you'll see in a few minutes, we use nanoparticles to actually deliver conventional therapeutics. Just try to get those therapeutics to work a little bit better than they normally work. And so you might want to release a conventional drug or use that nanoparticle to tell you whether the patient actually is sick in the first place. If they have a cardiac blockage, you want to find that blockage, identify it, see it on the X-ray more effectively. And then finally, just go away and don't leave a mess. And this is really the key thing, which is, okay, you don't protect yourself. Isaac Asimov said the robot, once it's done doing what it's done and helping all people, it just goes on and keeps cruising around. Actually, we don't want that to happen in nanotechnology. In fact, if it doesn't do its job in the body, you're going to pee it out eventually. It's going to get in the environment. So whatever we make, even if it does stay too long in the body, eventually it will get out. And it'll get in the environment, and we don't want it to be messing or leaving a pollution or any toxic byproducts anywhere in the body or in the environment. And so really what that means in our field is the structure has to degrade. We have to make them fall apart. And so, as I mentioned, there's a couple of examples of nanoparticles that are actually used currently or have been used. Abraxane is the cancer therapeutic I referred to. It's used for breast cancer. It's a nanoparticle, and it actually, I'll just give one quick insight into that. This little red dot here is some artist's conception of what a molecule looks like. So how many chemists believe that? Okay, so that's supposed to be the molecule. They load it into this nanoparticle, and then the nanoparticle goes into the body. And for some reason, which I don't have time to get into, that nanoparticle actually will find its way more selectively to the breast, the tumor in the breast, than into the kidneys or the liver or other parts of the patient's body. And in fact, this drug that's in there will not even get to the breast tumor without being in a nanoparticles. It's so low solubility it can't find its way. It can't dissolve in the serum or get to that. So that's one of the real reasons we use nanomaterials, to try to chaperone conventional molecules into places where they normally wouldn't want to go. So this is the cartoon that shows it. And how you do that, really, when you talk about targeting things, this is now work that comes from a collaboration that I have with Sangeeta Bhatia, who's on this coast at MIT, and Erkki Ruoslahti, who's at the Burnham Institute in San Diego, across the hall from us. This is a little nanoparticle. It's got a chemical species, what we call a cyclic peptide. And that peptide, that molecule, then specifically finds the tissues. Erkki likes to refer to them as vascular zip codes. It's a molecule that actually, the body has zip codes. They're tissues that have specific characteristics everywhere in your body. If you just find the right molecule to unlock that zip code, that molecule may stick to that part of the tissue in preference to other parts of the tissue. And then finally, the kind of go away and do and don't leave a mess is really ultimately this kind of thing. It's just a cartoon again of a silicon-based nanoparticle that we work with. We primarily work with silicon in the body mainly because it's a very soluble material, and actually the body knows how to handle it. Actually, there's more silicon in your body than there is in your cell phone. A chip in your cell phone weighs about 0.4 grams, and each of us, if you're about my height, you get about 0.5 grams of silicon in your body. And it's in this form right there, orthosilicic acid. So these two chemical equations, the only chemistry you'll get tonight, tell you that the nanoparticle will oxidize, that's here, and then that oxide dissolves and goes away. So when you're done, you basically made sand. And that's really the bottom line for that. There's some data, gratuitous data slide that shows that it works. I don't have time to talk about it. Okay, I do want to say one thing though, in my negative 10 seconds I have to talk here. If you have any kids, send them to UCSD. This guy here, actually I doubt there's anybody here in the room, but there's a guy named Chris Piester who's a professor at UC Berkeley. He was an undergrad about in the late 80s, early 90s. And then he had a kid, that's Kaiser Piester, and he's now a second generation UCSD. Both those guys did undergrad research at UCSD, Chris in the engineering department, unfortunately, and Kaiser in, actually Kaiser's in the chemistry department. Why do I show this picture? This is actually an image from what I call a summer school for silicon nanotechnology that I run. Some of those guys are high school kids. This guy, Preetam, he's going to MIT now. He's a high school student. Ga, she's at Harvard. She's a high school student also. Most of them are undergraduates, UCSD undergraduates. I use that as a training program. One of the problems we've ran into, that I've run into, and none of us have run into, as Pradeep told you, we really are strongly focused on research at UCSD, and it's a strong focus on getting you guys into the lab and getting you exposed to the excitement of research. And one of the challenges I ran into many years ago was a lot of undergraduates just don't know when to start. They don't know how to get into that, engaged in that activity. And so I said, okay, I'm gonna do summer school. So I do the summer school every summer. Students spend 6 weeks. We give them kind of a really intensive training, not like what you get in freshman chem lab. How many people took freshman chem lab? Okay, was it the worst experience of your life? It probably still is, believe me, it still is. Why? You're doing stuff that somebody did 50 times before. Nobody's ever, got this thing to not work, right? I mean, so it's boring. So I call these discovery projects. These guys work on projects that are going to be published in papers. They're doing the experiment for the first time and getting that excitement of the discovery and learning how research really works. And that's how we try to build that network of undergraduates. And hopefully, again, if you have any kids now, you want to send them back to UCSD, but you don't want them to go there for college, that's fine. Just send them for the summer. Okay, you're all kind of guaranteed enrollment because you're part of us, you're part of the alumni. And I'll leave it with that. Thank you very much.